Hello and welcome. My name is Phil Tuma. I'm an application development specialist in 3M's Electronic Materials Solutions division. Jamil Shah joined our group about a year and a half ago after doing his postdoc at UT Arlington, subject of immersion cooling. And I'm going to talk today about recent developments in immersion cooling with fluorochemical fluids and how these fit into the Open Compute project. I'd like to start by talking about how the immersion cooling subgroup fits into the Open Compute project, and how the differences between hydrocarbon and fluorochemical fluids are affecting the documentation that they're generating. Similarly, there are significant differences between single-phase and two-phase applications that have an effect on design recommendations and best practices. I'll give some real-world examples of fluorochemical deployments, including some large crypto mining deployments that suggest real cost of ownership merits for Hyperscale. And I'll wrap up by talking about some of the supply chain evolution that is enabling the use of immersion cooling. The chart at left shows how the immersion cooling workflow fits into the OCP project. Its goal is to define inclusive standards that allow the adoption of immersion cooling in the OCP community. Table 1 at right here is showing how different immersion technologies can be categorized based on the heat transfer mode, whether it's single or two-phase. The convection mode, do we have a pump or is it passive? The containment method, is one server enclosed in a clamshell or are there many servers together in a tank? And lastly, the fluid chemistry, be it fluorochemical or hydrocarbon. It turns out the heat transfer mode and the fluid chemistry have a pretty dramatic effect on the types of documentation that the immersion cooling subgroup is attempting to generate. So I'm going to talk more about those. But first, for those of you unfamiliar, the figure in the lower left is showing a typical single-phase tank and installation. You can see the liquid flows into the bottom of the tank, flows through the server, and the warm liquid flows through the coolant distribution unit and transfers heat to facility water. The tanks shown in that image are from an exascalar deployment of supercomputing hardware in Japan. Each tank is about 120 kilowatts, and I'll show you a little later what that hardware looks like. The system at right is a two-phase immersion deployment, 250 to 500 kilowatts in each tank, and the fluid is boiling off of the heat-generating devices. The vapor that's generated moves up and condenses on a coil, transferring heat to facility water. The condensed vapor then falls back to the tank. So this is what we would call passive two-phase immersion. As we look at commercially significant heat transfer fluids, there are a variety that can't be used for immersion cooling. Aqueous coolants, for example, tend to be very poor dielectrics, and they're usually corrosive. There are many flammable materials we don't use. Chlorinated and brominated organics tend to be ozone depleting, and many of them have a pretty substantial tox profile. So we're left with hydrocarbon fluids shown here at the bottom. The hydrocarbon structure has important implications for material compatibility and combustibility, as I'll explain. And one way of mitigating some of those effects is through the addition of fluorine. And we arrive at fluorochemicals that tend to be more inert and stable, but it's considerably more expensive as well. The hydrocarbon fluids that are used for immersion cooling are usually characterized as oils. And the reason for this is really straightforward. As I look at the chart on the right, I've ordered the hydrocarbons according to their molecular weight. And I've used alkanes here as representative of the class just because it simplifies the discussion. But at the bottom of the scale, you have a fluid like methane, which is, of course, a gas at room temperature and not very useful for immersion. Hydrocarbon pentane might be used for two-phase immersion. It has a right boiling point, but it's very flammable. And even hexane, which is at the high end of what might be useful for two-phase, is very flammable. You have to go to carbon numbers of 10 or more before the hydrocarbon is classified as combustible and therefore safe for immersion. And going up from there, you eventually run into oils that are simply too viscous to be pumpable and useful for immersion. Now, the low vapor pressure of these oils means that they're much easier to contain, but it also means that the hardware is oily when it comes out of the tank, and it tends to be a little more messy. Fluorochemicals shown on the right, again, we have perfluoromethane at the bottom, not very useful for immersion. Perfluoropentane has the right boiling point and is in fact used for two-phase immersion. At the high end of the two-phase regime is perfluoroheptane, which is also interestingly used for single-phase immersion. And its advantage is that it's got a far lower viscosity than any hydrocarbon oil, and therefore performs better. But it also means that there's less drag out when the hardware is removed from the tank. There's less fluid clinging to the part. And because the fluid has a high vapor pressure, it evaporates pretty quickly and cleanly, making it a lot easier to use. This tendency of fluorochemicals to evaporate kind of points to the fact that they have an environmental fate that differs from the hydrocarbon oils. Fluorochemicals, in fact, evaporate to the atmosphere. In fact, they partition to the air and atmosphere. And this can have environmental implications. Some of the fully fluorinated fluids have very high global warming potentials. Hydrocarbon fluids, on the other hand, should they spill, tend to partition to groundwater. And these environmental considerations are important for the immersion cooling subgroup as they ponder, spill cleanup and remediation methods. Hydrocarbon and fluorochemical fluids are very different from a material compatibility standpoint. The polymers that comprise a computer system are generally hydrocarbon in nature. And for this reason, hydrocarbon fluids tend to have more of an affinity for these polymers. Fluorochemical fluids, on the other hand, really only have an affinity for other highly fluorinated materials, and these are rarely used in computer equipment. For this reason, hydrocarbon compatibility assessments tend to focus on what we call first-order compatibility issues, the fluid's direct effect on the material. Will the fluid swell an elastomer, for example? Fluorochemical compatibility assessments tend to be less concerned with first-order effect of the fluid on the material. We look more at the material's effect on the fluid and on each other. We could, for example, have a hose that leaches plasticizer into the fluid, and that plasticizer can in turn cause an O-ring to swell. And this brings us to the subject of fluid hygiene and purity. If these fluids are going to pick up contaminants in the system, and they all do, how do we remove these contaminants? It's challenging to do with hydrocarbon fluids because they are chemically very similar to the materials we're trying to remove. Fluorochemicals, on the other hand, can be scrubbed in situ to a very high purity with activated carbon. And as an end result of that, used fluid is often as clean as the day it was put in. As mentioned earlier, the immersion cooling workstream is also working on design recommendations. And these can be pretty strongly affected by whether the application is single phase or two-phase. Single phase design uses pretty traditional methodologies. After all, air cooling is immersion cooling, and so we can use the same CFD tools to model the flow of fluid through the server as we use for air. Similar techniques can be used to instrument and control the flow fields within a server. Fluid containment is facilitated by the fact that the single phase fluids generally are not very volatile, and so the tanks don't need to be perfectly sealed, for example. They're relatively simple mechanical designs. Fluorochemical design specifically tends to focus, for reasons mentioned earlier, on fluid purity, how to scrub the fluid and make sure that hydrocarbon contaminants are not causing secondary effects on different materials within the hardware. Two-phase design considerations are not as familiar to most engineers. We have no finned heat sinks, for example. Instead, we use a boilerplate on the CPUs and GPUs. And you'll see an example of one on the right. This one is designed to go on an Intel Skylake socket. And what one finds is that its performance is not dependent on the flow field or the inlet temperature. It's really only dependent on the boiling temperature of the fluid. And the resultant case temperature is simply a function of the CPU power. And you can see in this example, the case temperatures are well below the case temperature specifications for the various Skylake SKUs, even though the fluid they're submerged in is boiling at 56 degrees Celsius. So thermal design is in many ways very simplified. It doesn't matter whether I put one of these or 25 of these in a chassis, they're all going to perform similarly. On the other hand, fluid containment is more challenging. The tanks are generally designed to operate at atmospheric pressure, and keeping them there requires knowledge of thermodynamics and psychrometrics that most of us have forgotten since school. Material compatibility, in a way, it's simplified because the fluorochemicals are very inert, but it's also complicated by the fact that we are essentially distilling the fluid on every one of these processes. Any non-volatile contaminants that are dissolved in the fluid can precipitate by distillation on the boiling surfaces, and these can follow the surfaces and hindering thermal performance. So fluid hygiene is extremely important in two-phase applications. Moving on now to some real-world deployments. I mentioned earlier the exascaler deployments in Japan. These supercomputers have actually totaled many megawatts, and they're interesting because of the unprecedented power density involved. You see it right there, an image of some of the compute hardware being unfolded on the table. They eventually got to a fluid usage of only 2 liters per kilowatt, which was really at the wall, at the limit of what they could do with single-phase immersion. Alibaba has deployed more than 2,000 servers in a single-phase deployment. You've heard it discussed in the OCP project. It's allowed them to show at a statistically meaningful scale some of the advantages relating to reduced noise, increased reliability, higher efficiency, etc. A 20,000 server deployment is planned for the coming year. The largest fluorochemical deployments have been two-phase and in the specialized market of Bitcoin mining. And at the top right, you see a facility built by Bitfury just outside of Tbilisi. It's a 40 megawatt facility that was built in about 6 months back in 2015. It's the integration of the company, Bitfury, that allowed them to extract real value from two-phase immersion technology. Because they make their own chips, their own boards, their own tanks, and their own facility, they were able to extract value at every step, and eventually went on to produce a 120 megawatt facility you see at lower right. TMG Core moved rectifiers outside of the tank, eventually reaching less than 1 liter of fluid per kilowatt, unprecedented power density. And all of these deployments share floor space density on the order of 35 kilowatts per square meter and very low PUEs. These crypto mining deployments, partly for their scale and partly for their cost sensitivity, suggest that there may be real cost of ownership merits for immersion cooling in the area of hyperscale compute. A couple of years ago, you may have heard us present at the OCP Summit on a paper study that was done comparing free air cooling to two-phase immersion cooling. It assumed a 30 megawatt hyperscale project in Des Moines, Iowa. 10 kilowatt air-cooled rack was assumed. The immersion-cooled racks were based on a 150 kilowatt allied control design that used a server built by Gigabyte for GPU compute, and Tier 3 assumptions were used. The study suggested as much as a 44% reduction in the CapEx attainable through the use of two-phase immersion. A lot of the savings was in the area of mechanicals through the elimination of chillers, but there was also substantial savings attributable to reduced telecom and fiber optic cabling, and a very simplified power distribution methodology. There were annual savings, of course, in the electricity through reduced PUE, and the elimination of roughly 300 million gallons of water per year through the use of dry coolers in place of adiabatic coolers. Hyperscalers and others have taken the study and built upon it, made their own tweaks, and they inevitably conclude there's real savings to be had with two-phase immersion. This won't be attainable without some evolution. One of the primary areas relates to the density of the hardware that's been immersion cooled. If we take a conventional air-cooled x86 server, it requires roughly 30 to 40 liters per kilowatt to submerge that IT. Some of the supercomputer projects that have been done have gotten to half of that, and Exascaler, as I mentioned earlier, has really pushed the limits down to about 2 liters per kilowatt. In crypto mining, we're down below 1. But even in the area of GPU compute today, with off-the-shelf GPU hardware, we can get as low as 5 to 10 liters of fluid per kilowatt. This is still nowhere near the entitlement. It's been demonstrated in a laboratory where we've cooled 1 kilowatt with as little as 200 cc's of fluid. As I mentioned earlier, the supply chain is not as clean today as we'd like it to be. There are a lot of sources of contamination, as I'll mention in a moment, that are really unnecessary for immersion cooling. And lastly, the tank designs are going to need to be refined. Things like adsorbent traps are being used already to drive fluid losses from two-phase applications to very low levels. This chart shows the most common sources of fluid contamination in modern computer equipment. Certainly the largest is PVC insulation, which is commonly used to insulate wiring, cabling, etc. It would be nice to see an alternative use, something like polyolefin. It contains less extractables. Do we really need UV stabilizers or flame retardants in an environment like immersion cooling? It's a good question. A lot of these materials are used in rectifiers, silicone RTV, hot melt adhesives. They're really not necessary at all. If we clean the solder flux from the boards and choose clean elastomers, it's not difficult to get to a system that would have 95% reduction in fluid contamination. It should be our goal in the OCP community to drive the supply chain in that direction. There are, of course, implementation considerations as well, maintenance and ergonomics. People commonly express concern about moving hardware in and out of the tank. This can be managed in some cases by building lightweight, smaller servers, perhaps half a U, a third of a rack width, so they can be easily managed by a person, or using robotics as TMG Core does in some of their designs. The path from production, testing, to deployment will of course look very different with immersion-cooled hardware. But vendors like Longwind are already stepping up, providing test equipment and validation tools that can be used to bring hardware to production. A person wanting to deploy two-phase immersion today would be hard-pressed to do so without a turnkey system commercially available, and these are emerging. Bitfury Allied Control, for example, has partnered with Gigabyte to produce very high-density GPU-based systems for HPC. TMG Core has done a similar thing with their Auto platform. 16 GPU node is shown here, but it's really a very agnostic platform with 6 kilowatts of 48-volt power and fiber optics that will enable the use of any hardware inside of that chassis. WeWin, lead ODM, has used their unique skills to densify the hardware to provide a turnkey cloud system. And Turbine Air Systems has a unique approach that allows them to modulate the tank pressure during operation so that the temperature of the hardware can be changed. So in closing, the immersion cooling subgroup is doing a great job of capturing in their workflow and documentation the differences between fluorochemical and hydrocarbon fluids, and the differences between single and two-phase applications. If you haven't already done it, I encourage you to go out and look at the work content. It's really the first time this stuff has been gathered together in one place. For those of us who do fluorochemical immersion, we've seen a real evolution since the Cray days, not only in the single phase, hyperscale and supercomputing deployments, but the trend from crypto mining towards cloud and hyperscale for two-phase immersion. And immersion cooling of all flavors will enjoy the materializing supply chain. Cleaner materials, more compact designs are the key to the success of immersion cooling. And I will close with a call to action. If you're a vendor of materials or components to the compute industry, I encourage you to contact us and learn about this oxalate extraction technique. It's a method we use to assess the compatibility of materials for immersion cooling. It allows us to quantify exactly how much extractable substance is in a material. And this is information that's useful not just for us, but for all flavors of immersion cooling.
Okay, very good. I'll begin by addressing a question for Jamal. He asked about maintenance. How long should we wait for the fluid to cool down before opening the tank and accessing the servers? It's a common misconception that we do need to power down the hardware to access the servers. That's not in fact the case in either single phase or two-phase immersion cooling. It's actually much better to perform swapping and servicing operations while the fluid is boiling in two-phase applications, for example. The fluid losses are dramatically lower because the hardware is removed from the tank completely dry. Someone asked about maintenance. Do immersion cooled systems require more or less personal maintenance and intervention? They're particularly interested because data centers in recent weeks have had to reduce their on-site staffing levels. It's a good question, an excellent one. You'll hear Alibaba talk about their single-phase deployments and the various merits of immersion technology. They talk about enhanced reliability. I can only assume that translates to reduced interventions, but I can't be sure. We are, after all, the fluid manufacturer, but Allied Control has more than 160 megawatts deployed and certainly would be a good reference as well for asking questions like that. Someone else asked, are there any arguments for the different applications with differences in density and or permittivity between hydrocarbons and fluorochemicals? I would say possibly if you're referring to electrical permittivity, certainly hydrogenated fluids tend to have slightly higher dielectric constants and maybe more likely to have, for example, signal integrity issues for very high-speed signals. However, by and large, I would say permittivity differences are not that substantial between hydrocarbon and fluorochemicals. The density differences are dramatic. Some fluorochemicals are twice as dense as hydrocarbons, for example. It's also true that electronics are far more dense than either, if you look at them on a volume displacement basis. And so when one thinks about what do you want on a data center, you want electronics. They're the densest of all. So the key to getting reduced mass and floor weight loading, for example, is to increase the density of the hardware so there are more electronics per unit volume, less fluid. Harold Miyamura asked about boilerplates. Who are the best contacts for technical development and information? There are now a variety of companies making boilerplates. Avid, which is now a division of Boyd Corp, is one of them. Cooler Master is another. AVC, Sunan have also made boilerplates. I could certainly connect with you afterwards, Harold, and provide some contacts with those companies.
One another comment is from David Smith is one alternative to new board chip designs would be to use fluid direct ring structures to both saving fluid and promote high density stakes, and OCP might consider. So this is one of the appeals that we also want to make with this OCP platform, that immersion cooling, especially two-phase immersion cooling, can deal with extremely high power densities. And definitely if we can significantly reduce the form factor of the server and specify that according to the fluid and make it like kilowatt per liter or kilowatt per volume, then that would be a great start. And OCP should definitely consider that.
I see a question by Nishi. It's very similar to one that was asked earlier. How do you handle replacing faulty DIMMs or other components? Again, I'm going to speak to two-phase immersion because I think in single-phase immersion, people are maybe more familiar. Whether it's fluorochemical or hydrocarbon, servers are simply lifted from the tank and typically operated on above the tank, so that any wet liquid can drip down. In two-phase, it's very different. This is counterintuitive to most. Again, the fluid is refluxing. It's a chemical engineering term, meaning that it's boiling and condensing in a refluxing fashion. So when the hardware is pulled from the liquid, it moves through a saturated vapor zone, and the liquid that remains on the part flashes and is captured by the condenser coils. The end result is that the hardware comes out almost completely dry, maybe just a few grams of fluid remaining. So it's very easy to perform servicing operations, and it needn't be done over the tank. It can be done externally or nearby. I hope that answers that question. Mark Shaw asked a question for two-phase. You said somebody got to 0.2 liters per kilowatt. Did I get that right? That was a laboratory experiment with a board that had 20 200-watt CPU simulators on it, Mark. It was, in fact, a 4-kilowatt board that was 17 by 20 centimeters, and it was cooled in less than 1 liter of fluid. So, yes, it was 200 cc's per kilowatt. That's an extreme example. Of course, it can't be built. We'd have no computing hardware today that's that dense. But again, we have seen 1 liter per kilowatt in crypto mining. Someone else asked, is there a ASHRAE Technical Committee 9.9 coordination on this fluid? The answer so far is no. I would say that was a succinct answer, right? ASHRAE TC 9.9 is concerned with other things like temperatures of cooling water and things of that nature, I believe. We've been peripherally involved in that work, but not the fluid chemistries themselves. cost of, someone asked, Shlomo, asked, what would you say is the cost of the fluid cooling for 30 kilowatts? Again, Shlomo, it gets back to density. If you submerge a standard conventional off-the-shelf air-cooled server, it requires 30 to 40 liters to submerge 1 kilowatt. And this is, 300 times perhaps what we need from a thermal standpoint. So the cost of the fluid today, in cloud applications, it can be prohibitive. In supercomputing applications, less so because the hardware value goes up. And that's certainly true in GPU computing where the hardware value is extremely high and it's relatively easy to densify. At that point, the fluid cost becomes almost insignificant relative to the hardware cost. Key asked if any evaporated gas leaks out of the system, if any evaporated gas leak on the system, may lose fluid continuously without leak detection system. The tanks, as you might have guessed, and I'm going to refer specifically to two-phase because I think that's what your question is about. The tanks are, of course, sealed during operation, and the vast majority that have been built are operated at atmospheric pressure, but they are quite well sealed. So fluid is not lost continuously during operation. But there are systems in place to prevent that. For example, in large hyperscale deployments and crypto mining, refrigerant monitors are used in the rooms housing the tanks. This is the same refrigerant monitors that are used in equipment rooms for centrifugal chillers and such. They're there to determine if a leak has occurred and to monitor the concentration in the room continuously. When those systems are used in hyperscale deployments, we find background levels exceedingly low, less than 1 part per million in the room. And so if the tank should rupture, which is one way a tank could catastrophically lose a lot of fluid, those systems would immediately detect it and report through facility communications. Shlomo asked whether we have a priced case study. We do, Shlomo, and there's a high-level version of it published in a few different places. I'd be happy to provide you an in-depth version. I know that TMG Core has also recently published a total cost of ownership analysis for their turnkey systems. What is the rationale for your customers to move to immersion? Is it extremely high density and better PUE? Ishi asked. It depends on the customer, of course. Density in and of itself rarely has much value, although in some supercomputing application there are certainly signal integrity implications of moving things closer together. The primary motivation, at least in the cloud space, has been reduced cost. For edge applications, it seems it's going to be more related to packaging density and low PUE, ability to operate in hot climates without evaporative cooling, for example. So it depends a bit upon the application. Luis asked if there's anywhere where I could read on the different cooling fluids as fluorochemicals and oils. 3M has published various papers on the different fluid chemistries, and we can connect afterwards. I could provide you some references and papers. And there's certainly a lot of information, at least on 3M fluid chemistries on the 3M website. And Luis also asked about the relative performance, presumably of different fluids. And I think he's asking a comparison between fluorochemicals and oils. There, Luis, it would depend very much upon the density. For example, in a single phase cloud application today, where we have 30 liters, or excuse me, maybe 30 kilowatts in a tank, pump power demands are not very high, and performance at that density will be very good with single phase, whether it's hydrocarbon or fluorochemical. It's when you start getting up to 100 plus kilowatts, perhaps per rack volume, that you start to see the performance of single-phase immersion, be it oil or fluorochemicals, drop off. And it's there that two-phase immersion, which shines out even at low density, is really going to shine out, because the PUE that you achieve is totally independent of density, unlike single-phase technology. So if you can achieve 1.05, for example, at 20 kilowatts a rack, you'd do the same thing at 500 kilowatts per rack. Key asked, is there any schedule to issue universal fluid specification? I could defer that to Jamil, who's on the OC committee. Personally, we have no plan to introduce a universal fluid specification. Different fluids, there are, for example, about 3 different chemistries that are used today in immersion cooling, 3 different fluorochemical chemistries. And they differ a little bit in how they behave, and it would be possible to break those down perhaps into different subsegments and provide specifications for each. Shlomo asked, does anyone have a two-phase performance system out there? I would encourage anyone in the audience from our partners to answer that question. As I kind of alluded to in the presentation, Shlomo, the largest deployments today have been in cryptocurrency, which is, of course, a niche application enabled by the complete integration of the companies that build them. The challenge in transitioning to x86 has been the lack of high-density hardware and a supply chain that's tailored to immersion. But there are certainly big fluorochemical deployments. I mean, you could talk with Alibaba, for example. You could speak with the folks in Japan, Exascaler Computer Systems, for example. Tony asked about the range of fluid chemistries available, pros and cons. I have a nice one-pager that kind of summarizes this, Tony. I can provide you afterward. And we'd be happy to talk more about it. I think we finished. Thank you, everyone.